a supervolcano that is a continent killer, and it blows every 600 to 800,000 years, and everyone dies. We're all going to die.
The ground over this iconic park is rising, and it's sparking a lot of questions and concerns. Is the supervolcano that lies beneath Yellowstone about to erupt? This intriguing and somewhat alarming phenomenon has captured the attention of scientists and nature enthusiasts alike, leading to a deeper investigation into what's really happening beneath the surface. The phenomenon of the ground rising is not entirely new to Yellowstone. The park sits atop a massive volcanic system, one of the largest in the world. This volcanic system is responsible for the park's geothermal features, including geysers, hot springs, and fumaroles. The rising ground is caused by magma accumulating beneath the surface, which is part of the natural cycle of the Yellowstone caldera. According to geologists, the Yellowstone caldera is a supervolcano that has erupted 3 times in the past 2.1 million years. Each of these eruptions was catastrophic, covering large areas of North America with ash and affecting the global climate. However, it's important to note that the last major eruption occurred long time ago. Since then, there have been smaller eruptions and periods of ground uplift, but none have been catastrophic. The current ground uplift is part of this ongoing volcanic activity. Scientists have been monitoring Yellowstone's ground movements for decades using a variety of tools, including GPS, seismographs, and satellite imagery. These tools allow scientists to detect even the smallest changes in the ground's elevation and to track the movement of magma beneath the surface. One of the key reasons for the recent uplift is the movement of magma into the magma chamber beneath Yellowstone. This chamber is a vast reservoir of molten rock that lies several miles below the surface. As magma moves into the chamber, it causes the ground above to rise. This process is similar to inflating a balloon, where the increase in pressure causes the surface to expand. However, the rising ground does not necessarily mean that an eruption is imminent. While the current uplift is significant, it is not a definitive sign that Yellowstone is about to erupt. In fact, Yellowstone has experienced similar uplifts in the past without erupting. For example, in the 1980s, the ground over Yellowstone rose by several inches over a period of a few years, but no eruption occurred. Scientists believe that the current uplift is part of the natural cycle of the Yellowstone caldera. The magma chamber periodically inflates and deflates as magma moves in and out. This process is driven by the heat and pressure generated by the Earth's mantle, which lies beneath the magma chamber. The movement of magma is influenced by a variety of factors, including tectonic activity, changes in the Earth's crust, and the buildup of gases within the magma. The process of magma accumulation and ground uplift can be understood by examining the mechanics of how magma behaves. Magma, a molten mixture of rock, minerals, and gases, is generated in the Earth's mantle. Due to its lower density compared to the surrounding solid rock, it tends to rise towards the surface. As magma moves upward, it can accumulate in large underground reservoirs known as magma chambers. When enough magma enters these chambers, the pressure increases, causing the overlying rock to bulge and the ground above to rise. This uplift is usually gradual and can be detected using sensitive instruments such as GPS and INSAR, interferometric synthetic aperture radar. These tools have allowed scientists to monitor the ground deformation in Yellowstone with remarkable precision, providing crucial data on the behavior of the underlying magma. Interestingly, the current uplift at Yellowstone is not unprecedented. Historical records and modern measurements have documented several episodes of ground deformation in the area. For instance, from 2004 to 2010, the ground in the Yellowstone caldera rose by about 27 centimeters, approximately 10.6 inches, which was attributed to the influx of magma into shallow reservoirs. Despite these significant uplifts, no volcanic eruption occurred. It's important to understand that ground uplift in volcanic regions is not unique to Yellowstone. Similar phenomena have been observed in other volcanic systems around the world, such as in Hawaii, Iceland, and Italy. These regions also experience periodic ground deformation due to the movement of magma. In many cases, the uplift does not lead to an eruption, but is instead a part of the ongoing volcanic processes that shape our planet's surface. The monitoring of ground uplift and other signs of volcanic activity at Yellowstone is conducted by the Yellowstone Volcano Observatory, YVO, a collaborative effort involving the U.S. Geological Survey, USGS, the University of Utah, and the National Park Service. The YVO employs a comprehensive network of seismometers, GPS stations, and other instruments to keep a close watch on the caldera's activity. This extensive monitoring allows scientists to detect any significant changes that could indicate an increased likelihood of an eruption. In conclusion, while the rising ground over Yellowstone is a fascinating and noteworthy phenomenon, it is a natural part of the caldera's life cycle. The current uplift is caused by the accumulation of magma beneath the surface, a process that has been occurring for millions of years. Although this activity is closely monitored, it does not necessarily mean that an eruption is imminent. Understanding and studying these geological processes helps scientists to better predict and prepare for potential volcanic events, ensuring the safety and knowledge of future generations. As I said before, Yellowstone has experienced similar uplifts in the past without erupting. For example, from 2004 to 2010, the ground rose significantly, but eventually subsided without volcanic activity. This historical context helps experts maintain a cautious yet non-alarmist view on current events. The caldera's geological complexity plays a role too. Magma can move between deep underground chambers, causing ground uplift without reaching the surface. This natural cycle is influenced by tectonic forces and the Earth's mantle dynamics. Volcanic processes at Yellowstone operate on geological timescales, spanning thousands to millions of years. Significant changes like ground uplift can occur without immediate consequences. The Yellowstone Volcano Observatory, YVO, continuously monitors seismic activity, ground deformation, and gas emissions, providing comprehensive data to understand the caldera's behavior. In summary, while the rising ground at Yellowstone is noteworthy, it doesn't necessarily indicate an imminent eruption. Yellowstone has experienced similar uplifts in the past without erupting. According to researchers, the last major eruption occurred over 640,000 years ago. Since then, smaller eruptions and ground movements have occurred, but none have been catastrophic. These historical uplifts provide valuable data, helping scientists understand that uplift alone doesn't signify an imminent eruption. Continuous monitoring and advanced technologies allow researchers to detect subtle changes, ensuring any potential threats are identified early. While the current ground rise is significant, it fits within the park's long history of geological activity, and there's no immediate cause for alarm. The current uplift is a reminder of the powerful forces at work beneath our feet. However, the likelihood of a major eruption in the near future remains low. Scientists use various tools to monitor Yellowstone's activity, including GPS, seismographs, and satellite imagery. These instruments provide precise measurements of ground deformation, seismic activity, and gas emissions. By analyzing this data, experts can better understand the dynamics of the Yellowstone caldera and predict potential changes. The ongoing research and monitoring efforts are crucial for ensuring public safety and advancing our knowledge of volcanic processes. Continuous research helps scientists understand the dynamics of the Yellowstone caldera. This ongoing monitoring provides valuable data, allowing experts to detect any significant changes that might indicate increased volcanic activity. Through the use of advanced technology and comprehensive data analysis, researchers can make more accurate predictions and prepare for potential hazards. The collaborative efforts of geologists, volcanologists, and other scientists ensure that any unusual activity is quickly identified and assessed. This vigilance helps maintain the safety of visitors and residents while contributing to our broader understanding of volcanic systems. It's fascinating to consider that Yellowstone sits atop one of the world's largest active volcanic systems. The park's stunning landscapes and geothermal features, like geysers and hot springs, are a direct result of this underlying volcanic activity. These features draw millions of visitors each year, eager to witness the raw power of nature. Despite the potential risks, Yellowstone remains a captivating and relatively safe destination. The park's unique geothermal activity not only shapes its landscape, but also provides invaluable insights into the inner workings of our planet. Despite the recent ground uplift, Yellowstone remains a safe and incredible destination for nature lovers. Visitors can explore its unique geothermal features, enjoy its diverse wildlife, and marvel at its breathtaking scenery. The park's beauty and geological significance make it a must-visit location. Park officials and scientists work diligently to monitor and manage any potential risks, ensuring a safe experience for all. The continuous study of Yellowstone's dynamic geology enhances our understanding of volcanic activity, while allowing visitors to appreciate the awe-inspiring natural wonders it offers. So, should you worry about Yellowstone erupting? The short answer is no for now. While it's important to stay informed and aware, Current scientific evidence suggests that an eruption is not likely in the foreseeable future. The rigorous monitoring and research efforts by scientists provide reassurance that any significant changes will be detected early. Yellowstone's ground uplift is a natural phenomenon, part of its geological cycle. Embrace the wonder and beauty of this magnificent park, knowing that experts are keeping a vigilant watch over its dynamic processes. We hope you enjoyed learning about the fascinating geology of Yellowstone. If you love nature documentaries and want to stay updated on the latest discoveries, make sure to subscribe to our channel. We truly value our viewers and strive to bring you the best content. Your feedback and engagement mean the world to us. If you have any questions or topics you'd like us to cover, please leave a comment below.
Attention, attention. This is an emergency message. Yellowstone National Park employees and guests, residents of the surrounding area. This is an official emergency message from the Federal Center. Please listen carefully and follow all the instructions.
Imagine waking up to a world where the sky turns dark, ash rains down like snow, and panic spreads faster than the lava beneath Yellowstone. "Yellowstone has erupted!" the headlines scream. This isn't a scene from a disaster movie. It's a very real possibility. What would happen next? From immediate devastation to long-term global chaos, we'll explore the terrifying reality of a Yellowstone supervolcano eruption. This is one scenario you can't afford to ignore. And while you're watching, if you have any video suggestions, be sure to leave a comment below. Yellowstone National Park, spanning across Wyoming, Montana, and Idaho, is one of the most iconic natural landscapes in the United States. Famous for its geothermal features, including geysers like Old Faithful, hot springs, and bubbling mud pots, Yellowstone sits atop a massive volcanic hotspot. But beneath the park's stunning beauty lies a sleeping giant, the Yellowstone supervolcano. Unlike typical volcanoes, which form steep-sided cones, a supervolcano like Yellowstone is characterized by a massive caldera, a large depression formed after a major eruption. The Yellowstone caldera measures about 30 by 45 miles, a testament to the sheer scale of its volcanic power. According to researchers, historically the Yellowstone supervolcano has erupted 3 times in the past 2.1 million years. Each eruption released vast amounts of ash and magma, significantly altering the global climate and environment. According to researchers, the most recent eruption, approximately 640,000 years ago, ejected over 1,000 cubic kilometers of material, creating the current caldera and impacting the Earth's climate for decades. The park's geothermal activity today is a constant reminder of the magma chamber that still lies beneath Yellowstone. Scientists closely monitor the area for signs of volcanic activity, using various techniques to track ground deformation, gas emissions, and seismic activity. Supervolcanoes, unlike their smaller counterparts, have the capability to produce eruptions thousands of times more powerful. The term supervolcano is used to describe a volcano that can produce an eruption with ejecta greater than 1,000 cubic kilometers. To put this in perspective, a supervolcanic eruption can discharge enough material to cover entire continents in ash and cause dramatic changes to the global climate. Supervolcanoes form over hotspots, areas where magma from deep within the Earth's mantle rises towards the surface. In Yellowstone's case, the magma chamber is estimated to be about 60 kilometers long, 30 kilometers wide, and up to 10 kilometers deep. This chamber of molten rock lies beneath the park, heating the surface and fueling the geothermal activity that Yellowstone is known for. A supervolcanic eruption occurs when pressure from the magma chamber builds to the point that the overlying crust can no longer contain it. This pressure is often caused by the accumulation of gases within the magma. When the pressure is finally released, it results in a massive explosion, ejecting vast amounts of ash, pumice, and volcanic gases into the atmosphere. Regular volcanoes typically have a central vent through which lava flows. In contrast, supervolcanoes often do not have a central vent. Instead, they have a large caldera, a depression formed when the ground collapses into the emptied magma chamber after an eruption. This caldera can be tens of kilometers in diameter. Yellowstone has experienced 3 major eruptions in its history, each shaping the landscape dramatically. The eruptions occurred approximately 2.1 million, 1.3 million, and 640,000 years ago. Each of these eruptions was far more powerful than any volcanic eruption in recorded history. Today, Scientists monitor supervolcanoes like Yellowstone using a combination of ground-based and satellite technologies. These include seismic activity, ground deformation, gas emissions, and hydrothermal activity. Earthquakes often precede volcanic eruptions as magma moves towards the surface. Changes in the ground level can indicate the movement of magma. Increased levels of volcanic gases like sulfur dioxide can signal an impending eruption. Changes in the park's geysers and hot springs can provide clues about what's happening below the surface. While predicting the exact timing of a supervolcano eruption is challenging, continuous monitoring helps scientists understand the potential signs of increased volcanic activity and provides valuable data to help mitigate the impact of such an event. Understanding the science behind supervolcanoes is crucial for preparing for their potential eruptions. The magnitude of their power and the far-reaching consequences of their eruptions make them one of the most significant natural threats to our planet. The study of supervolcanoes not only helps in disaster preparedness, but also provides insights into the Earth's geological processes and history. Supervolcanoes serve as a stark reminder of the dynamic and sometimes violent nature of our planet. Their eruptions, although rare, have the potential to reshape continents, alter climates, and affect life on Earth in profound ways. By studying supervolcanoes like Yellowstone, scientists hope to better predict and prepare for future eruptions, minimizing their catastrophic impacts on humanity and the environment. The immediate effects of a Yellowstone supervolcano eruption would be catastrophic, causing widespread devastation and chaos. As the superheated magma bursts through the surface, the eruption would begin with a massive explosion, sending ash, pumice, and volcanic gases high into the atmosphere. This initial blast would devastate the surrounding areas, obliterating everything within a radius of several miles. Pyroclastic flows, which are fast-moving currents of hot gas and volcanic matter, would sweep across the landscape at speeds of up to 700 kilometers per hour, incinerating everything in their path. Ash fallout would be one of the most immediate and widespread effects. The eruption could eject billions of tons of ash into the atmosphere, which would then spread across vast areas, potentially covering much of North America. Cities and towns downwind from Yellowstone could be buried under meters of ash, leading to the collapse of buildings, the clogging of machinery, and the contamination of water supplies. Inhalation of ash could cause severe respiratory problems and even death for people and animals in the affected areas. The massive injection of ash and sulfur dioxide into the atmosphere would create a volcanic winter, drastically reducing temperatures worldwide. The ash cloud would block sunlight, causing global temperatures to drop by several degrees. This sudden cooling would disrupt weather patterns, leading to shorter growing seasons and widespread crop failures. The reduction in food production could lead to severe food shortages and famine, exacerbating the humanitarian crisis. The eruption would also have immediate impacts on air travel. The vast ash cloud would make flying hazardous, leading to the grounding of flights across North America and potentially other parts of the world. Ash particles can damage aircraft engines and pose significant risks to air travel, as seen during the 2010 Eyjafjallajökull eruption in Iceland, which caused widespread flight cancellations across Europe. Infrastructure would suffer extensive damage. Power lines would be brought down by the weight of ash, leading to widespread blackouts. Roads and highways would become impassable, hampering rescue and relief efforts. Communication networks would be disrupted, making it difficult for authorities to coordinate responses and for people to contact loved ones. In the immediate aftermath, emergency services would be overwhelmed. Hospitals would be inundated with patients suffering from burns, injuries, and respiratory issues. The sheer scale of the disaster would stretch resources to their limits, making it challenging to provide adequate care and support to those in need. The environmental impact would be severe. Rivers and lakes could be choked with ash, killing fish and other aquatic life. Forests and farmlands would be buried, leading to the loss of wildlife habitats and agricultural land. The sulfur dioxide released into the atmosphere would form sulfuric acid droplets, leading to acid rain, which would further damage crops, forests, and bodies of water. Overall, the immediate effects of a Yellowstone supervolcano eruption would be devastating, with far-reaching consequences for both the local and global environment. The combination of explosive force, ash fallout, and volcanic winter would create a disaster of unprecedented scale, affecting millions of lives and causing widespread destruction. In the short term, a Yellowstone supervolcano eruption would have dramatic and far-reaching global consequences. One of the most immediate effects would be a significant drop in global temperatures, known as a volcanic winter. The massive amount of ash and sulfur dioxide ejected into the atmosphere would block sunlight, leading to a temporary cooling of the Earth's surface. This sudden drop in temperature could last for several years, disrupting weather patterns and leading to severe climatic changes. Agriculture would be heavily impacted by the volcanic winter. The reduction in sunlight and lower temperatures would shorten growing seasons and reduce crop yields worldwide. This would lead to food shortages and increase the risk of famine, especially in regions already vulnerable to food insecurity. The economic impact would be severe, as agricultural production declines and food prices skyrocket. Transportation would also face significant disruptions. The ash cloud would pose a major hazard to aviation, grounding flights, and disrupting global air travel. This would affect not only passenger travel but also the transportation of goods, leading to supply chain interruptions. The resulting economic losses from grounded flights and disrupted trade would be substantial. Health issues would arise from the widespread ashfall. Inhaling volcanic ash can cause serious respiratory problems, particularly for individuals with pre-existing conditions such as asthma or chronic bronchitis. The ash would contaminate water supplies, leading to further health risks from drinking and using contaminated water. The environmental impact would extend beyond immediate destruction. Acid rain, formed from sulfur dioxide in the atmosphere, would damage forests, crops, and aquatic ecosystems. This environmental degradation would have long-term consequences for biodiversity and ecosystem services. Overall, the short-term global consequences of a Yellowstone supervolcano eruption would be profound, affecting climate, agriculture, transportation, health, and the environment, leading to a cascade of challenges that the world would need to address urgently. The long-term global consequences of a Yellowstone supervolcano eruption would be profound and enduring, impacting various aspects of life and the environment for decades, if not centuries. One of the most significant long-term effects would be the persistent climatic changes resulting from the massive injection of volcanic gases into the atmosphere. The sulfur dioxide released would combine with water vapor to form sulfuric acid aerosols, which can remain in the stratosphere for years. These aerosols reflect sunlight away from the Earth, leading to prolonged cooling known as volcanic winter. The last major eruption of Yellowstone, which occurred approximately 640,000 years ago, caused global temperatures to drop by several degrees, and a similar event today could result in substantial cooling, disrupting climate patterns worldwide. This prolonged cooling would have devastating impacts on global agriculture. Shorter growing seasons and reduced sunlight would lead to consistent crop failures, causing widespread food shortages and increasing the risk of famine. The agricultural sector would struggle to adapt to the new conditions, leading to economic instability, especially in countries heavily reliant on farming. The decline in agricultural productivity would also impact the global economy, causing food prices to rise and exacerbating inequalities between different regions. The environmental impacts would be equally severe. Ecosystems that rely on specific climatic conditions would be disrupted, leading to loss of biodiversity. Forests, wetlands, and other natural habitats would suffer from acid rain, which is formed when sulfuric acid aerosols return to the Earth's surface. This acid rain would damage vegetation, soil, and water bodies, further stressing ecosystems already struggling to adapt to the new climate. The long-term recovery of these ecosystems would be slow, and some species might face extinction if they cannot adapt quickly enough. Human health would be another critical area affected by the eruption. The volcanic ash that blanketed large areas would continue to pose respiratory risks long after the initial eruption. Chronic respiratory conditions could become more common, particularly in regions closest to the eruption. Additionally, the contamination of water supplies with ash and acidic compounds would pose ongoing health risks, requiring significant resources to manage and mitigate. The social and political ramifications of a supervolcano eruption would also be profound. The strain on resources caused by food shortages, economic instability, and health crises could lead to social unrest and conflict. Governments would face immense pressure to provide aid and maintain order, and international cooperation would be crucial in managing the global fallout. The eruption could also lead to mass migrations, as people flee affected areas in search of more stable environments, further complicating the social and political landscape. Economically, the long-term impacts would be significant. The cost of rebuilding infrastructure, healthcare, and agricultural systems would be immense. Insurance companies would face unprecedented claims, and many businesses, particularly in the tourism and agriculture sectors, would struggle to recover. The economic shockwaves would ripple through global markets, potentially leading to a prolonged economic downturn. In summary, the long-term global consequences of a Yellowstone supervolcano eruption would be far-reaching and complex, affecting climate, agriculture, ecosystems, human health, social structures, and the global economy. The world would need to invest heavily in adaptation and mitigation strategies to cope with the new realities brought about by such a catastrophic event. In summary, the eruption of the Yellowstone supervolcano would be one of the most devastating natural events in human history. From the immediate cataclysmic effects such as pyroclastic flows, ashfall, and local devastation, to the far-reaching consequences like volcanic winter, global cooling, and massive agricultural disruptions, the impact would be unprecedented. The immediate aftermath would see widespread destruction and chaos, while the long-term effects would reshape global climate, economy, and society. Scientists continuously monitor Yellowstone and other supervolcanoes to better understand their behavior and to improve predictive models. While the exact timing of such an eruption remains uncertain, the potential consequences make it imperative to prepare and develop strategies for mitigation and response. Understanding the science behind supervolcanoes and the potential impacts of an eruption is crucial for global preparedness. Investments in monitoring, research, and international cooperation can help mitigate the catastrophic effects of such an event. As we continue to explore the dynamic and sometimes violent nature of our planet, it is essential to remember the power of nature and the importance of being prepared for the worst-case scenarios. If you found this video intriguing, don't forget to like, subscribe, and hit the bell icon for more fascinating content. Stay informed and stay prepared, because understanding our planet is the first step in protecting it. Imagine a world where Earth loses its magnetic field. What would happen? In this video, we'll explore the potential consequences of our planet's disappearing magnetic shield. Extending from Earth like invisible spaghetti is the planet's magnetic field. Created by the churn of Earth's core, this field is important for everyday life. It shields the planet from solar particles, it provides a basis for navigation, and it might have played an important role in the evolution of life on Earth. But what would happen if Earth's magnetic field disappeared tomorrow? A larger number of charged solar particles would bombard the planet, putting power grids and satellites on the fritz and increasing human exposure to higher levels of cancer-causing ultraviolet radiation. In other words, a missing magnetic field would have consequences that would be problematic, but not necessarily apocalyptic, at least in the short term. And that's good news because for more than a century, it's been weakening. Even now, there are especially flimsy spots like the South Atlantic anomaly in the southern hemisphere, which create technical problems for low-orbiting satellites. The first thing to understand about the magnetic field is that even if it weakens, it's not going to disappear, at least not for billions of years. Earth owes its magnetic field to its molten outer core, which is made mostly of iron and nickel. The churning outer core is powered by the convection of heat released as the inner core grows and solidifies, said John Tarduno, a geophysicist at the University of Rochester. The inner core grows by about 1 millimeter per year. This magnetic field engine, known as a dynamo, has been chugging along for billions of years. Scientists think that the current core arrangement may have settled into place about 1.5 billion years ago, according to 2015 research that found a leap in the magnetic field's strength around then. But Tarduno and his team have found evidence for a magnetic field on Earth in the planet's oldest minerals, zircons, dating back 4.2 billion years, suggesting that activity in the core has been creating magnetism for a very long time. It isn't clear why the dynamo got started, Tarduno told Live Science, though it's possible that the enormous planetary impact that created the moon might have been the key driver. This impact, which occurred perhaps 100 million years after Earth came together, could have shaken up any stratification or layering of materials in Earth's core. Imagine shaking up a bottle of oil and water on a planetary scale. This disruption could have promoted the convection that still drives Earth's dynamo today. Eventually, the inner core will probably grow large enough that convection in the outer core is no longer efficient, and the magnetic field will fail. But that scenario is so far off that it's not worth losing much sleep over. We're talking billions of years, Tarduno said. Compasses would do strange things. Compasses are really nothing more than tiny magnets, and like all magnets, they align themselves with nearby magnetic fields. Conveniently, Earth's magnetic field is strong enough to force compasses to align north to south. But with our planet's magnetic field gone, compasses would point to any nearby source of magnetism. Even an outcrop of magnetic rock could do the trick. In fact, scientists have documented this effect before. Magnetic anomalies, places on Earth where nearby natural magnetism cause compasses to malfunction, are found around the world. In the Central African Republic, for example, unexplained magnetic variations in Earth's crust cause compass needles to point in random directions, rendering them useless for navigation. If our planet's magnetic field disappeared, wandering compasses could become the norm worldwide. Birds couldn't migrate for the winter. Humans aren't the only animals that exploit Earth's magnetic field for navigation. Many birds, sea turtles, lobsters, honeybees, salmon, and even fruit flies have biological compasses, termed magnetoreceptors, built into their bodies. Birds use this ability to seek warmer climates during winter months, while sea turtles navigate the open ocean and seek beaches to lay their eggs. Scientists even think that most female sea turtles return to the same beaches every year, a feat made possible in part by their natural compasses. If Earth's magnetic field disappeared, many animals that depend on compass navigation could be in serious trouble. Sea turtles could literally get lost at sea. Migratory birds might fly in the wrong direction, threatening their survival. Honeybees might get lost trying to find their hives, which could impact the pollination of flowers and other plants. With their navigational abilities severely compromised, these and many other organisms could face extinction. The aurora wouldn't be the same. Along with our biodiversity, the loss of Earth's magnetic field could alter Earth's auroras, known commonly as the northern and southern lights. These beautiful phenomena are created when our planet's magnetic field channels charged particles from the sun, known as the solar wind, into our planet's upper atmosphere. The solar wind is usually deflected by our magnetosphere, the invisible shell created by Earth's magnetic field. But around the north and south poles, the magnetosphere dips inward like a funnel, allowing the solar wind to interact with our upper atmosphere. The result of this interaction are these spectacular, multicolored bands of glowing plasma known as auroras. Auroras on Earth have been known to shine so brightly, a person could literally read by them. But without Earth's magnetic field, our entire upper atmosphere would be exposed to the solar wind, completely changing how our auroras might appear. They could even resemble auroras found on Venus and Mars. Since these two planets have no significant magnetic fields, they sometimes have faint, less colorful auroras scattered across their night sides. Thus, along with altering our polar skies, the disappearance of our magnetic field could forever dampen one of Earth's most breathtaking natural wonders. Cosmic rays could reach Earth's surface. Our magnetic field doesn't just give us beautiful auroras, it keeps us alive. Cosmic rays and the solar wind are harmful to life on Earth, and without the protection of our magnetosphere, our planet would be constantly bombarded by a stream of deadly particles. The effects of cosmic rays on the body can be pretty terrifying. While on lunar missions, for example, astronauts often reported seeing flashes of light when they closed their eyes, the direct result of cosmic rays passing through their retinas. A few even developed cataracts years later. Radiation and cosmic rays are a real concern for NASA, especially when it comes to long-term spaceflight. Astronauts on a mission to Mars could undergo up to 1,000 times the exposure to radiation and cosmic rays that they would get on Earth. If Earth's magnetic field disappeared, the entire human race, and all of life in fact, would be in serious danger. Cosmic rays would bombard our bodies and could even damage our DNA, increasing worldwide risk of cancer and other illnesses. The flashes of light visible when we close our eyes would be the least of our problems. Widespread power outages and broken satellites. Human health is one issue, but without a geomagnetic field, our technology would also be at risk. Satellites can and do suffer damage from solar storms, and without Earth's magnetic field, every electronic device could be exposed to high-energy particles from cosmic rays and the solar wind. In fact, solar activity has caused such problems before. In 1989, a massive solar flare, an eruption of superheated plasma from the surface of the sun, slammed into Earth's magnetosphere and knocked out electricity in Quebec, Canada. The power grid for the entire province went offline for 12 hours, and other nearby regions scrambled to keep their grids working. Some satellites suffered damage as their delicate electronics simply weren't designed to handle a huge solar storm, and many tumbled out of control for hours after the flare struck. While the geomagnetic storm of 1989 was unusually massive, the solar wind is always hitting our magnetosphere, even during normal solar activity. If Earth lost its magnetic field, there would be no magnetosphere, and no line of defense, even from weaker solar storms. Our power grids would be more vulnerable than ever, and even our computers and other electronics could suffer damage if a solar storm struck. Our atmosphere could be stripped away. Perhaps the most horrifying effect of losing Earth's magnetic field might be losing the air we breathe. And the solar wind would once again be the culprit. The sun's natural wind is so powerful, it can easily rip gases out of a planet's atmosphere until there is little gas left at all. In fact, this likely happened to Mars. Mars was probably once a lot like Earth, with oceans of water and a thick atmosphere. But unlike our planet, its magnetic field disappeared billions of years ago. Its atmosphere was left totally unprotected, causing it to be ripped away into space. Once its atmospheric pressure dropped low enough, its water began to evaporate until it too was taken by the solar wind. It's quite possible that without our geomagnetic field, our atmosphere, our oceans, and life on Earth could suffer the same terrible fate. Thanks for watching. In the comments section, you can write your opinion about the video. You can also write if there is a topic you are interested in.
Imagine this. What happens if an asteroid hits Earth in 2024? A chilling thought, isn't it? So let's delve into this unnerving hypothetical scenario. Picture an asteroid, a colossal chunk of rock and metal, hurtling through the vast expanse of space. Now, these celestial marauders can range considerably in size. Some are as small as a pebble, while others can be as large as a small city. For this scenario, let's consider a sizable asteroid, say, about the size of a football stadium. And speed? Asteroids don't amble, they sprint. Speeds can reach up to 56,000 miles per hour. That's over 70 times the speed of sound. And when an object of such size meets such speed, the result can be quite devastating. Now, imagine this asteroid, this football stadium-sized chunk of rock and metal, hurtling at breakneck speed, is on a collision course with our home planet. The clock is ticking, and in 2024 it makes landfall. The impact, as you might guess, would be nothing less than cataclysmic. The energy released would be equivalent to billions of atomic bombs. The immediate vicinity would be obliterated in an instant, reduced to a smoldering crater miles wide. But that's not all. The shock waves from the impact would ripple across the globe, causing earthquakes and tsunamis far from the point of impact. Skyscrapers would crumble like sandcastles, and entire cities could be washed away. And then there's the dust. The collision would throw up an enormous cloud of dust and debris into the atmosphere, blotting out the sun for months, maybe even years. This impact winter would cause temperatures to plummet, crops to fail, and potentially lead to a mass extinction event, similar to the one that wiped out the dinosaurs. A lot depends on the size, speed, and composition of the asteroid, but one thing is clear: the impact would be catastrophic. So, what happens scientifically when an asteroid collides with our blue planet? Well, let's unravel this mystery together. First, we need to understand what we're dealing with. An asteroid, in essence, is a chunk of rock or metal, a relic from the early solar system. The size of these cosmic travelers can vary dramatically. Some are as small as pebbles, while others can be hundreds of kilometers in diameter. When an asteroid approaches Earth, it's moving incredibly fast, typically tens of kilometers per second. The energy it carries is colossal, akin to the most powerful nuclear weapons. And when it collides with Earth, all that energy needs to go somewhere, and fast. This energy release is the first major effect of an asteroid impact. In a split second, the kinetic energy of the asteroid is converted into an explosion of light, heat, and sound. This can vaporize the asteroid and a significant amount of the ground, creating a crater. The size of the crater depends on the size and speed of the asteroid, but it can be many times the size of the original object. But the story doesn't end there. The impact also sends shock waves through the Earth, which can cause earthquakes and tsunamis if the impact is near a body of water. And then there's the ejecta, the matter blasted out of the crater. This can be thrown high into the atmosphere, where it can block out sunlight and cause a nuclear winter effect. This is where the global climate effects come into play. The dust and aerosols in the atmosphere can block sunlight, leading to a drop in temperature. This can affect plant life and, by extension, the entire food chain. So, while the impact itself is destructive, the aftermath can be equally devastating. The effects of an asteroid impact extend far beyond the impact site. It's a global catastrophe. The Earth has weathered such events before, but it's a reminder of our vulnerability in the vast expanse of space. History has already given us a glimpse of what an asteroid impact can do. So let's take a trip down memory lane to about 65 million years ago, when a celestial object, known as the Chicxulub impactor, struck Earth with the force of billions of atomic bombs. This impactor, around 6 miles wide, came hurtling towards our planet and left a crater over 100 miles wide in what is now the Yucatan Peninsula in Mexico. The aftermath? A mass extinction event that wiped out around 75% of all species on Earth, including the dinosaurs. Imagine that, these colossal creatures who dominated Earth for over 160 million years were wiped out in what, in geological terms, was the blink of an eye. Now, let's fast forward to a more recent event, the Tunguska event of 1908. This incident involved a comparatively smaller asteroid, about 120 feet in diameter. It exploded over the remote Tunguska region in Siberia, with a force estimated to be about 1,000 times that of the atomic bomb dropped on Hiroshima. Despite its smaller size, the Tunguska asteroid flattened over 800 square miles of forest, and its shockwave was felt thousands of miles away. Thankfully, due to the remote location, there were no documented human casualties, but it served as a stark reminder of the destructive potential of asteroids. Both these events, the Chicxulub impact and the Tunguska event, have significantly shaped our understanding of asteroid impacts. They've shown us that size doesn't always matter when it comes to destruction, and that even relatively smaller asteroids can have catastrophic effects. The past has shown us the devastating potential of asteroid impacts, but could we survive one in 2024? That's the question we'll delve into next. So stick around as we explore the bleak aftermath of a hypothetical asteroid impact in our current era. In the aftermath of such an event, what would life on Earth look like? One might imagine a scene out of a science fiction movie, but the reality could be far more devastating. Picture this. An asteroid impacts our planet. The immense energy of the collision vaporizes the asteroid and a large portion of the Earth's surface, creating a crater many miles wide. Dust and debris are thrown high into the atmosphere, blocking out the sun. This is where the concept of a nuclear winter comes into play. The sunlight would be blocked out for months or even years. Without sunlight, photosynthesis would halt. Plants would die off, followed by the herbivores that rely on them, and then the carnivores that prey on those herbivores. The food chain as we know it would collapse. The oceans would not be spared either. The impact would cause massive tsunamis, wiping out coastal cities and marine life alike. The dust in the atmosphere would also cause a dramatic drop in temperatures, leading to a deep freeze across the globe. As for us humans, we would be facing a trio of calamities: the immediate devastation of the impact, the long-term effects of a nuclear winter, and the societal collapse that would likely follow. Infrastructure would crumble, resources would become scarce, and the societal norms we rely upon would disintegrate. Survivors would have to contend with a world that's vastly different from the one we know. We could expect mass migrations as people scrambled to find habitable zones. Societal structures would need to be rebuilt from the ground up, and the scarcity of resources could lead to conflict. In essence, we're talking about a mass extinction event, similar to the one that wiped out the dinosaurs 65 million years ago. The aftermath of such an event would be a world that's unrecognizable from the one we live in today. Life as we know it would change dramatically, possibly even cease to exist. Is there anything we can do to prevent such a disaster, one might ask? In this day and age where science fiction often becomes science fact, we've developed strategies to combat this celestial threat. Let's turn our attention to NASA's Planetary Defense Coordination Office. This group's mission is not straight out of a Hollywood blockbuster, but a very real and essential endeavor. They're our first line of defense, responsible for early detection of near-Earth objects or NEOs that could pose a risk to our planet. With a network of telescopes scanning the skies, they're our watchful guardians, identifying potentially hazardous asteroids years, even decades before any possible impact. But spotting these cosmic interlopers is only the first step. What can we do if we find a rogue asteroid on a collision course with Earth? Enter DART, the Double Asteroid Redirection Test. This mission, currently under development, is set to demonstrate a method of asteroid deflection known as a kinetic impactor. In simpler terms, DART plans to crash a spacecraft into an asteroid at high speed, nudging it off its path. It won't be a big change, but when done far enough in advance, even a small shift in trajectory can mean the difference between an asteroid hitting Earth or harmlessly passing by. Of course, these are early days, and much remains to be explored and understood. Space is vast and full of uncertainties. But the fact that we're taking steps, that we're not sitting idle, is a testament to human ingenuity and our will to survive. While the threat of an asteroid impact is real, so too are our efforts to prevent such a catastrophe. From detection to deflection, we're investing time, resources, and brainpower to ensure that if the worst-case scenario were to unfold, we wouldn't be caught unprepared. Today, we're not just dreaming of survival, we're actively working towards it.
The outer core is a boundary that's known as the Gutenberg discontinuity. According to EOS, the outer core is a liquid rolling mass of molten metal that surrounds the solid inner core. The inner core is found 3,200 miles below the surface of the Earth and is almost 1,550 miles wide, roughly the size of the Moon. For a while, it was believed that the Earth's core was a chunk of solid iron, but seismic measurements from as early as the 1950s suggested that it might contain more than just iron. The core is actually about 10% less dense than iron and most likely also contains, in addition to other elements, nickel, silicon, and magnesium. Sulfur is also found in the core, and it's estimated that roughly 90% of the Earth's sulfur is located there. And funnily enough, the current makeup of the core is actually younger than Earth itself, having formed between roughly 500 million and 1.5 billion years ago. Why is the Earth's core hot? Although it's known that the Earth's core is incredibly hot, no one knows exactly how hot it is. And National Geographic writes that the temperatures are liable to shift based on the core elements, the Earth's rotation, and pressure. Despite this, scientists have some guesses as to how hot the Earth's core actually is. Scientists estimate that temperatures there fluctuate between almost 8,000 degrees Fahrenheit to over 10,000 degrees Fahrenheit. According to FIS, with these temperatures, the Earth's core is even hotter than the surface of the Sun, which is just about 10,000 degrees Fahrenheit. But the highest temperatures actually occur at the Bullen discontinuity, which distinguishes the inner core from the outer core. Scientific American reports that there are three main reasons that the Earth's core is so hot. There's the heat that comes from radioactive decay, the heat caused by differentiation, or the friction generated by heavy objects being pulled to the core, and the heat that's left over from the initial formation of the planet. But in the end, scientists are unsure exactly how hot the Earth's core is. Not only is there still debate about what exactly the core is made out of, but it's incredibly difficult to do an experiment in the lab that faithfully simulates conditions in the Earth's core. Scientists have come up with their current best estimates using lasers and high-pressure devices, but the exact melting point of iron at high pressures is still unknown. The lopsided effect. Everyone considers the Earth to be a sphere, so it stands to reason that its inner core would be similarly spherical. But in fact, the Earth itself isn't even perfectly round. According to Scientific American, the Earth more closely resembles a sphere that is squashed at its poles and swollen at the equator. The core is similarly squished, but rather than growing in a uniform fashion, the core actually grows in a lopsided way. According to the print, the Earth's core, which is already growing slowly as it cools, turns out to grow more quickly on one side than the other. In 2021, new research suggested that the inner core is losing heat faster under Indonesia than it is under Brazil, and that quicker cooling on one side would accelerate iron crystallization and inner core growth on that side. However, due to the immense gravity at the center of the Earth, the growth of the core ends up being distributed so that its radial growth remains constant at 1 millimeter per year. Ultimately, it's unknown exactly why this cooling process happens faster under Indonesia than under Brazil. But EarthSky writes that scientists believe that this process has been occurring ever since the Earth's core was formed. And interestingly, it's possible that the rotation of the Earth has an effect on the iron crystals in the core, which appear to be aligned along the rotation axis of the Earth, despite the fact that they would theoretically be randomly aligned. Why might the Earth's core cool down? Despite being incredibly hot, the Earth's core is actually going through a constant process of melting and freezing. According to Gizmodo, when the tectonic plates move and one of the plates gets pushed underneath the other, a process known as subduction, the mantle ends up losing some heat. And as the plate sinks deeper and deeper into the mantle, it takes heat from the core as well. But while this is happening, some of the other tectonic plates are actually creating more heat since they're so big that the mantle underneath them is hotter than average. This heat also travels down to the core, but instead of cooling it down, it heats it up and reactivates the melting process. However, according to the conversation, despite this continuous process, the Earth's core is ultimately cooling down, albeit incredibly slowly as it's been doing ever since it formed. And as the core cools down, the inner core actually ends up growing since solid iron has more volume than liquid iron. This means that every year the inner core grows by about 1 millimeter. But even this cooling process gives off heat that travels all the way to the Earth's crust through the process of convection. This type of cooling process likely won't affect life on the surface for billions of years, since it'll take over 1 million years for just 1 mile to cool down. But what if the core suddenly cooled down all at once, losing our magnetic field? If the core suddenly cooled down, one of the very first things that would happen is the loss of the planet's magnetic field. According to Cosmos magazine, the magnetic field around the Earth is created by the outer core, which in addition to being liquid is constantly rotating through heat-driven circulation. Known as the dynamo effect, this theory suggests the constant flow of metal in the outer core creates electric currents. And as the Earth rotates, these electric currents create a magnetic field that extends around the entire planet. If the magnetic field around the planet disappears, not only will birds be unable to migrate and compasses will cease to point north, but all life on Earth will suddenly become more exposed to solar winds. While this doesn't mean the end of all life on the planet, it does mean much higher exposure to radiation, which can be dangerous to humans, but some animals withstand radiation better than others. Without a magnetic field, technical glitches will also become commonplace, since solar particles can cause interferences with high-frequency radio waves, according to Live Science. The Earth's magnetic field is absolutely vital towards protecting the planet's atmosphere, but don't worry. While movies like The Core make it seem like the second the magnetic field falters that laser-like sun rays will burn the Golden Gate Bridge into two, the real effect wouldn't be as dramatic. Although, if there happens to be a particularly bad solar flare, who knows? Stopping the motion of the plates. Another effect of the Earth's core cooling down would be that the tectonic plates would cease moving. If the core cooled down, it would in turn cool down the mantle upon which the tectonic plates travel. But it isn't just the liquid mantle that moves the plates around. The heat from the core itself is also thought to move the Earth's plates. UChicago News writes that scientists once believed that the Earth's plates moved because of the negative buoyancy created as they cool. However, it's now believed that the plates move due to the heat that they draw from the Earth's core. According to Science Advances, scientists estimate that as much as 50% of the movement of the tectonic plates is driven by heat from the core. Without this heat, it's possible that Earth will become a completed jigsaw of titanic slabs that will no longer drift or sink, writes National Geographic. Without moving plates, subduction will also cease to occur, and although there may be occasional earthquakes due to the crust melting off into the mantle, as the inside of the Earth cools, the outside would come to a virtual standstill. And one important implication of this finding is the idea that if the heat coming from the core has an effect on the surface, then it's possible that there's even more heat stored in the core than previously believed. Starting to look like Mars. If the Earth's core cooled, after some time our planet would begin to resemble some of the other planets in our solar system. As the crust melts into the mantle slowly, the minor earthquakes and additional pockets of volcanism would start to make Earth's surface resemble that of Venus, according to National Geographic. As everything slowly comes to a grinding halt and the lack of a magnetic field causes solar winds to irradiate and microwave the planet, the surface of the planet would start to resemble Mercury. But according to space, it's more likely that the planet would end up looking like Mars, which itself once had shifting tectonic plates that were likely similar to the ones on Earth now. Because Mars never had its own magnetic field, or if it did, it faded out extremely early, its outer layer was always vulnerable to solar winds. And as the planet cooled, its plates also became stationary, resulting in the planet's stagnant and rocky surface. However, the planet may not actually be as motionless as initially thought. According to Science Daily, in 2012, scientists discovered that there are likely active faults on Mars, but it's unclear if they are actually active more than once every million years. And while some scientists believe that the movement could come from magma or water underneath the surface, others think that it's due to the planet's ongoing cooling and contraction. How long till the Earth's core cools? Ultimately, nothing lasts forever, and the Earth's core is included in that. And ever since the core formed between 500 million and 1.5 billion years ago, it's been steadily cooling, even if it's at an infinitesimally slow rate. According to Interesting Engineering, since most of the heat at the Earth's core is released through radioactive decay, the core will likely stay warm for longer than if most of the heat was primordial, meaning residual heat from the formation of Earth. But even with all of these heat sources fading, it's still going to be a very long time before the Earth's core cools down naturally, with estimates ranging from tens of billions of years to upwards to 90 billion years from now. Luckily, since the sun's likely going to burn out in around 5 billion years, according to space, the Earth won't even be around to see its core fade away. Could we heat the Earth's core back up? If the core suddenly cooled down, would it even be possible for humans to do anything about it? The movie The Core makes it seem doable, but in reality, traveling to the Earth's core is insanely difficult. From the surface of the Earth to the center is a distance of about 4,000 miles. And according to Scientific American, the deepest hole ever dug by humans only goes down about 7.5 miles. Known as the Kola Super Deep Borehole, the hole took almost 20 years to dig and was meant to go as deep as possible, which the scientists estimated would be about 9 miles. But after the team encountered rocks at 356 degrees Fahrenheit, they were unable to go any further since this was almost twice as hot as they'd predicted. But even if the core suddenly cooled down to the point of being able to travel through it, temperature isn't the only thing keeping humans away from the center of the Earth. Spring writes that the pressure at the center of the Earth measures at around 364 GPa, gigapascals. In comparison, atmospheric pressure on the Earth's surface is around 101325 PA, Pascal. This means that the pressure at the Earth's core is almost 3.5 million times higher than surface pressure. Even the pressure at the bottom of the ocean is only 1,000 times higher than surface pressure, so going to the center of the Earth would really be one high-pressure situation. What else could happen to the Earth's core? Although it's unlikely that the Earth's core is going to cool down anytime soon, that doesn't mean that it'll quietly keep chugging along until it's time to fade away. Over the years, scientists have actually discovered that the core may be leaking into the mantle, and it may have been leaking for billions of years. While the inner core is estimated to be at most 1.5 billion years old, since it's estimated that the magnetic field already existed 3 billion years ago, according to Science Focus, it's likely that there was some semblance of the outer core already at play. And in 2019, scientists started to realize that the core may have been interacting with the mantle earlier than once assumed and leaking tungsten isotopes into the mantle, reports EOS. And in 2020, Science Alert writes that scientists also discovered that the core might also be leaking iron into the mantle. However, no one really knows what such a leak means or how long it's been occurring for. All anyone knows is that a leak from the core to the mantle under high temperature and pressure is possible, and it could explain why mantle rocks hold so much more iron than meteorites. But whether or not this leak will have any negative effects in the future is unknown, and if the leak got bigger, humans probably wouldn't be able to do much about it. Thanks for watching. To stay updated on the latest discoveries, make sure to subscribe to my channel and turn on notifications.